Hi all, this is my video number 4 on differential equation. We still deal with sturm system, which is of the form we have Ly, which can be written as P y prime plus Qx y is equal to minus lambda r x y. Yeah, and of course you can rewrite that, put it the right hand side to the left hand side. Subject to the boundary condition, we have alpha ya plus beta y prime a that equal to 0, and gamma yb plus, you see, delta y prime b that equal to 0. Okay, so in the last video I have given you the definition of self-adjoint and the definition of orthogonal of two distinct solutions of sturm system, and as well as the orthonormal. Okay, now for this video I will start with a theorem. We have a theorem, right? If y1 and y2 are, let's say, distinct eigenvalue, two distinct eigenvalues, sorry, lambda 1, yeah, not y, but lambda 1, lambda 2. Let lambda 1, lambda 2 are two distinct eigenvalues, which means lambda 1 is different than lambda 2, yeah? Lambda 1 different than lambda 2, and we have the eigenvalue, then the corresponding and the corresponding eigenfunction y1, y2. Okay, so if the problem is self-adjoint, if the problem is self-adjoint, then y1 and y2 are orthogonal with respect to weight function Rx on interval AB. Okay, the self-adjoint, what is self-adjoint? I have defined what is self-adjoint, which is we integrate from the endpoint AB, u LV minus v LU must equal to 0. So this is the definition of self-adjoint problem. Now, how to prove this? Remember that we deal with the sturm system. Yeah. Now, how to prove this? If we take from that definition, right? So I can say, let's say, because we have y1, y2, yeah, from the theorem is the eigenfunction corresponding to the lambda 1, lambda 2 eigenvalue. So I can write those operator Ly as Ly1, this is equal to minus lambda 1 r y1, and Ly2, this is equal to minus lambda 2 ry2, where is a function of x on AB. Okay, so if I multiply that with y1 and I multiply that with y2 and I multiply that with y1, and then we subtract each other, so what we have is that y2 we multiply by operator L1, and the other one we multiply by y1 L y2, and it's end up with you can check from there. This is we multiply by y2, we multiply by y2, so those y1, y2 and r can be factored out. What left is lambda 2 and lambda 1, so we have lambda 2 minus lambda 1 r y1 y2. Yeah, so we can always do this. Yeah, we can always do, because y1 and y2 are eigenvalues, y1 and y2 are eigenfunctions, so it must satisfy those equations. So that's why we can write that way. And this y1 y2, this y1 y2 belong to C2 in AB. I think you have familiar with this kind of notation. C2 means y is twice differentiable and continuous. Okay, now if I integrate, right, so if I integrate this from A to B, so what we have, yeah, integrate from A to B, so what we have, we integrate from A to B, yeah, y2 ly1 minus y1 ly2 dx. This is just integrate the right hand side. We have lambda 2 minus lambda 1. To integrate AB, we have r y1 y2 dx. Now from here you can see that since lambda 2 lambda 1 are distinct, which means since lambda 1 different than lambda 2, so we have lambda 2 minus lambda 1, this is different than 0, but this must equal to 0, right? This is from the 0 because it's from the system itself. You can see from the system. Okay, so since that cannot be 0, what left is, yeah, from this, since this is not equal to 0, then what left is this part must equal to 0. So we have integrate A to B r y1 y2, this is equal to 0. All right, so therefore y1 and y2 are orthogonal. Okay, so that's the proof for that. And we have another theorem. We have another theorem. The eigenvalue has no complex eigenvalues. Yeah, the eigenvalue problem. The eigenvalue problem has no complex eigenvalue. Okay, so to prove this, so let's say we have a problem that has a complex eigenvalue. Yeah, the problem has complex eigenvalue. So what happened? So which means I can write that lambda naught as the eigenvalue as a nu naught plus I mu naught. Okay, mu naught plus I nu naught, where mu naught is different than 0. Okay, and the corresponding eigenfunction and the corresponding eigenfunction, we have y naught is equal to, let's say, u naught plus I v naught. This is the corresponding eigenfunction. Then, since y naught is the eigenfunction, means it satisfies the sturm liouville system. So which means I can write that. So then we can write that p y naught prime plus q y naught. This is equal to, or you can write this is plus lambda naught r y naught that equal to 0, subject to the boundary condition alpha y naught a plus beta y naught prime a that 0 and gamma y naught b plus delta y naught prime b equal to 0. So why we can write like this? Because y naught is the corresponding eigenfunction for the eigenvalue lambda naught. So which means y naught must satisfy the sturm liouville system. So if I take the complex conjugate of those, then the complex conjugate of y naught, which is y naught bar, I can write like that, so must also satisfy the sturm liouville system. So we can write that as a p y naught prime bar plus q y naught bar plus lambda naught bar r y naught bar that equal to 0. This is for the complex conjugate. Okay, as well as the boundary condition. So we have alpha y naught bar a plus beta y naught bar prime a that equal to 0 and gamma y naught b plus delta y naught prime b that equal to 0. So you can see that since y naught satisfy the system, the sturm liouville system, which means that y naught bar, which is the complex conjugate of y naught, which is u naught minus I v naught, is also the eigenfunction of the problem. And with respect to eigenvalue, with respect to the eigenvalues, lambda naught equal to nu naught minus I mu naught. Okay, mu naught minus I nu naught. So from the previous theorem we have integrate a to b r y naught bar dx. That gives us integrate ab r y naught squared dx. Okay, because if y, we have y2 y2 y1 are different or distinct eigenfunction, then it must orthogonal. So in this case, we show that this is equal to 0. Alright, but this is impossible because since r positive and y is not a trivial solution, yeah, y naught is not a trivial solution. If it is a trivial solution, then it is not the solution for the sturm-liouville and sturm-liouville system. So it's not a trivial solution, so which means this is impossible. So this equation, let's call this equation star. So star is impossible. So our assertion that the problem has a complex conjugate is in contradict from what we have. So therefore the system has no complex conjugate. Okay, so this system or this theorem said that if the self-adjoint problem has eigenvalues, then it must be real. Yeah, but by the way, this is not guaranteed the existence of the eigenvalue. Alright, so with that I go to another theorem we have before we go to the little bit example. You have theorem. So any eigenvalue problem, has two alternatives. Either you have every complex number are eigenvalues. Just a minute. Every complex numbers are eigenvalues. Or the eigenvalues form one countable set without finite limit. One countable set without finite limit. So what does it mean? So in this case, which means that we have the eigenvalue. I can write eigenvalue in terms of lambda 1, lambda 2, and so on, such that if we take a limit n goes to infinity lambda n, this goes to infinity. Okay, let's see an example. We consider the self-adjoint eigenvalue problem. Okay, self-adjoint eigenvalue problem. Which is y double prime plus lambda y equal to 0. Subject to the boundary condition, we have y0 equal to 0 and yc equal to 0. Okay, in this case, we have our ly is given as y double prime. So with this, if we integrate our limit from 0 to c, because we want to self-adjoint is we have integrate ulv minus vlu, this is equal to 0. Okay, so we want to show this is equal to 0. We want to show that this problem is eigenvalue problem, a self-adjoint eigenvalue problem. So if we integrate that from 0 to c, using those definition L, U, V, and so on. So what we have here is V Lu minus U Lv dx. Then you can use integration by parts, that you can split those things to make life easier, I guess. Lu dx minus integrate 0 to c u lv dx. Okay, and then you use the integration by parts. What is integration by parts? I put it here. So we have integrate u dv, this is uv minus integrate v du. Okay, in general, this is the integration by part. So you use the integration by part for both of this integral. Then you're going to have for this you have v u prime minus integrate 0 to c u prime dv, and for that one we have u v prime minus integrate 0 to c v prime du. Okay, so rearrange those things. So you're going to have v u prime minus u v prime. Okay, we evaluate from 0 to c plus integrate 0 to c v prime du minus u prime dv. This of course 0. So what left is that this, if we use the boundary condition here, if you use the boundary condition, we plug vc is 0. Okay, uc also 0, u0 is 0, so that gives you 0. So therefore we can show from here this eigenvalue problem is self-adjoint. Yeah, it satisfies that integrate from 0 to c vlu ulv is 0. Okay, so therefore the problem is self-adjoint. So therefore the problem is self-adjoint. Now from here I think you can find yourself how to find the eigenvalues. Yeah, eigenvalues. And in fact I have given in the previous lecture, in the previous videos, that the eigenvalue for that problem is given as lambda n is equal to n pi over c squared, and the corresponding eigen function yn is sine n pi over c x for n 1, 2 and so on. You can try that. You can try that by yourself. And the previous theorem on the orthogonality of the uh, eigenfunction for the self-adjoint eigenvalue problem, orthogonality of eigenfunctions for the self-adjoint eigenvalue problem, assert that we have integrate from 0 to c. From there, if we consider y1, y2, or yn, ym, two different eigenfunctions, so we have sine m pi cx, sine n pi cx dx. So this is the odd function, sine. With that, if you evaluate this thing with the boundary condition you have above, then this give you 0. For m different than n, and Rx we consider as 1. For all x in 0 c. So therefore, in this case, yn, ym are orthogonal. So therefore, yn and ym are orthogonal. What about if n equal to m? I think I just I leave it to you that part. Okay, for n equal to m to see what happened. It's not difficult to show what happened there. Okay, so before I end up this video, I think I'm going to give one more theorem. I'll give you another theorem. Okay, eigenfunction and eigenfunction of sturm-liouville system. You know, when I say sturm-liouville system, is unique except for a constant factor, except for a constant factor. So how to prove this? Proof: if we let u and v be a eigenfunction, let u, v be eigenfunction corresponding to a single eigenvalue, lambda naught, say. Okay, so we shall show that u is actually u and v is linearly dependent. We show that u and v are linearly dependent. So if you're linearly dependent, which means I can write u in terms of, let's say, kv or something like that. V is just multiple, u is just multiple of v, which is not the case, because the eigenfunction, it must be different, because we have different eigenvalues. We have distinct eigenvalues. So since uv satisfy the boundary condition, since uv satisfy the boundary condition at x equal to a, so we have alpha UA plus beta U prime A, this is equal to 0, and alpha VA plus beta V prime A that equal to 0. And alpha beta cannot be 0. Alpha squared plus beta squared, this is different than 0. And if you could take the Wronskian of UV, yeah, Wronskian, of UV, yeah, so we have WUV, that gives us, this is UA, U prime A, VA, V prime A. Okay, so this is 0. This is 0. So which means that if the Wronskian is 0, there must be U and V, means U and V are linearly dependent. So that is given. So therefore U and V are linearly dependent. So which means that if they are linearly independent, so we can write U in terms of that. So in other words, if for the eigenvalue problem, the eigenfunction is unique. You cannot have basically for a certain of specific eigenvalue, you cannot have two different eigenfunction. Okay, so I think with that I end up my video here. So as a conclusion, I conclude that what we have done today, in this video, that I give you the theorem on the orthogonality of y1, y2. If y1, y2 self-adjoint, then y1, y2 are orthogonal with respect to certain weak function. And I also proved that the eigenvalue problem has no complex eigenvalues. And I give you example on the how to show that the self-adjoint, or the given eigenvalue is self-adjoint, and end up with the last theorem that I mentioned just now. So with that, I thank you. Bye.